Jnanam Paramam Dheyam. Knowledge is supreme.
Okay, so just towards the end of the last lecture, I just talked about the measurement, which is probabilistic in the sense that you take a large number of identically prepared systems, and then if you want to measure a specific energy En, then the value will be mod Cn squared, which is what is the probability for finding the energy En, right? Everybody is there, that is where we kind of stopped. So, recall the definition of psi. You just insert an identity operator which is in parenthesis here on the same side, and then the coefficient Cn is nothing but the inner product of phi n with psi. Everybody with me? We did this. Okay, so then if you want to find the expectation value of a system prepared in a state psi, then Hamiltonian expectation value of the energy, then it will be weighted average, where mod Cn squared is the probability for this energy En to be measured, and so on. So, you sum it over and that will give you the average energy. So, what have you learnt in classical mechanics? You have a phase space. Phase space is defined by position and momentum, right? And then you have dynamical variables, which I have called it as capital A, capital B, which are functions of this x and p. Then if you want to know the time evolution, Hamiltonian helps in finding the time evolution in classical mechanics. What are those equations? First, you need to write the Poisson bracket of A and B, which is governed by the Poisson bracket of x and p being, you all know Poisson bracket, right? Okay, the definition of a Poisson bracket of two variables in a phase space defined by x and p involves these partial derivatives in this fashion. So, that is the definition. If you want to find what is the Poisson bracket of x and p here, so del x by del x is 1, del p by del p is 1, del x by del p is 0, del p by del x is 0. So, it is just 1. So, I am just trying to bring in some kind of a correspondence between a Poisson bracket which is learnt in classical mechanics with commutator in quantum mechanics. That is the main motivation why I am going and comparing and contrasting classical mechanics with quantum mechanics. Okay, so this is the formal definition of this Poisson bracket, and evolution equations depends on the Hamiltonian, and you can write x dot dx by dt involving the partial derivative of the Hamiltonian is also a dynamical variable which is dependent on x and p. So, you will have an equation which gives you the time evolution of the position coordinate, another equation which gives you the time evolution of the momentum, right. What is these equations called? Hamilton's equations. Okay. So, these two equations in classical mechanics, this one is called Poisson bracket, and these two equations which I have written, which gives you the evolution in phase space, time evolution, they are called Hamilton's equations. So, now we want to see an analogy to quantum physics. So, you clearly see that here the phase space time evolution is governed by some equation. We also want to write the state vector which we write in quantum mechanics to be governed by some equation, that is one. And what will be the analog of Poisson bracket when you go to quantum mechanics? So, those are the questions you can ask, and so the first thing is all the dynamical variables, example your Hamiltonian and other operators which are functions of x and p, they get promoted to become operators in Hilbert space. To be more precise, you can take linear operators in Hilbert space. Poisson bracket which we had, you can replace that by a commutator bracket. What is a commutator bracket? A commutator of A comma B is AB minus BA. Okay. A and B are Hermitian operators. Let us take them to be corresponding to observables. Is commutator, when you do the commutator, what happens? So, suppose I want to find a dagger of this. Someone, what is this? So, B dagger, sorry, BA minus AB, is that right? That is nothing but minus of commutator of A with B. So, something bothering us, if we have two observables which are Hermitian operators, the commutator is not a Hermitian operator, right? If you want to make it Hermitian, what do we do? Suppose I call this to be C operator, then it is not Hermitian. What do I do? Yes, multiply by an I, and then this dagger, that I will also get in here. So, minus I. So, you will get this to be again an IC. So, these are the reasons why you will have an I here, because your left hand side is not going to be Hermitian. If you want to make both left hand side and right hand side to match, you put an I factor. Why an H cross? Why do you need a H cross? By dimensional arguments, the Planck constant is the relevant one for the product of X and P, which you can introduce. Okay. So, this is one naive way of arguing why it is postulated that the Poisson bracket goes to commutator bracket, and the commutator bracket is IH cross delta J. You are done for a finite dimensional Hilbert space. Is that right? You proved this for a finite dimensional. But if you have a commutator of A with B is I times C, then what happens? So, C in fact here is an identity operator, right. So, if you take X operator with P operator, let us do one dimensional, that will be IH cross identity operator. In general, it could be an infinite dimensional space. If I take the trace on both sides, what will the left hand side be? Left hand side is 0 by this property. Is that correct? Then what is the problem? Tell me. Is this allowed? This contradicts. Left hand side is not equal to right hand side, right? So, which means this identity is valid only for finite dimensional linear vector space. That is the only way you can try and say that this is in the infinite dimensional vector space, you cannot have this. In general, if you have an AB commutator as IC, you have to impose what? Even in the finite dimensional Hilbert space, if this side is 0, this should be traceless matrices, okay, right. If I want this, take trace, if this is 0, this implies C is traceless in finite dimensional Hilbert space. But in infinite dimensional Hilbert space, this property cannot be satisfied, because you can't give a matrix representation, even though we can write a Dirac bracket notation, you cannot write a matrix representation to argue that trace AB is equal to trace BA in an infinite dimensional Hilbert space. So, that is just a. There is also something else we could prove. Delta A is your standard deviation of an operator A. What is the formal definition? We saw this in one of the lectures. What is delta A? It is the expectation value of A squared minus expectation value of A the whole squared, and then you take the square root. So, for some dynamical variable or some operator, the standard deviation is given this way. Product of 2, this is what we call it as an uncertainty in A. Standard deviation is what we call it as an uncertainty in the observable corresponding to the operator A times the uncertainty in B. Can be proven that this is going to satisfy, it's going to be related to the commutator bracket. The commutator was 0, then what does it mean? What does Heisenberg's uncertainty principle tell you? You always write delta A, delta B is greater than or equal to h cross by 2 or something, right? What does that mean? Delta x, delta p, when you write, you say that if you can precisely look for the position which is delta x, your delta p will be very large, right. So, this is what is, you cannot simultaneously measure x and p. If the commutator of A and B is 0, then delta A, delta B is 0. So, you can simultaneously measure both of them with precision if the commutator is 0. So, XP commutator is what? XP commutator is non-zero. Okay. So, because XP commutator is non-zero, you have an uncertainty principle, which is your familiar Heisenberg's uncertainty principle. In general, if two operators are commuting, that is this one is 0, then you can show that those two can be simultaneously measured. Is that clear? There is no uncertainty that measuring one will not give you precise value for the other one. This we will prove in one of the tutorials. Okay. So, hence non-zero commutator of two operators will imply uncertainty principle, and we can say one is precisely measurable, the other one may not be precisely measurable. So, these are some things which you can play around. This I already said. If you take the conjugate and transpose of two operators, so what we showed that the commutator of A comma B is same as negative of commutator of A comma B dagger, right. So, it is not Hermitian. To make it Hermitian, we introduce an I. For XP commutator, you need a dimensionless constant. XP commutator, whatever is the dimension, you have to introduce Planck constant so that the both sides dimensions are matched. And some of the interesting properties of the commutators, which one of the things which you should remember, if you remember when I was saying the properties of operators on the linear vector space, linear operators, the order matters, the order matters. You can't say whether I call AB and BA are one and the same. AB is different from BA in general. When will it be same? When the commutator of A with B is 0, then the order will not matter, or you can measure this or that in whichever order, right. So, you need to keep track that you can't violate the order. So, if A, B, C, D is the order, I first do the expansion of this side, I take the A out and B commutator with CD, and then this one I keep the A, but since this one should be the order as AB, the B should come this side. B cannot be here, which you can do in your classical mechanics, but in quantum mechanics, A will be to the left, B will be to the right. Okay. And what else can we do? We can further do the CD also the same way. So, CD also if you do it, what happens? C comes to the left and D goes to the right. Okay. So, it will become AC with B and D, and you can also write A with BC commutator and D this side. These are the two terms which you will get from this term, and similarly the other two terms you will get from. One way in which you could do is you can expand this as ABCD minus CDAB, right. You could do that. And you can also verify that I can write this as A times B with CD plus A times CD, sorry, A times CD and then put the B here, right, this one. And you can explicitly write this further as AC times BD. This term will allow one more term which is A with BC times D. Similarly, this term will be A with C dB plus A with D B. Where will the C go? In the left. This is clear? Is the pattern clear to you? This is the way to play around with the commutator brackets when you have products of operators. Okay. Suppose I give you x squared commutator with p squared. How will you do that? X squared commutator with p squared. Now there is one more thing you can use here. X with x, there is no order, right? You can use that fact here. The commutator of x with x is 0. So this is not AB, it is not two different operators, the same operators. So how will we write this? We can write this as x with xp squared plus x with p squared x. And then what do we do? So that is x hat with x p hat with p hat plus x hat p hat, sorry, x hat p hat x hat with p hat. Okay, that is the first term. The second term will be x with p hat x hat plus p hat x hat p hat x hat. And now you use xp to be IH cross, right? I am doing it in one dimension. What is the simplification finally? xp twice xp and then twice xp with this one will be px, right? Twice px IH cross, that's it. So there is something which you see here, the beauty, what is happening. This xp with px should have the property that it is Hermitian, right? Like that day I was telling you that the order matters, and whenever I have to write a Hermitian operator, So, this if you have taken A with B as C, the C should be same as C dagger, right? And you can verify that if you take this operator, 2 factor anyway, let us not worry. If you take xp with px and take the dagger of it, it will be same as, this will become px plus xp, which is same. And we did not do anything, we just used the commutative property, and we see that it always comes as a symmetric combination, which I was trying to insist last time, that in quantum mechanics, because the order matters, when you have a dot product of two operators, you first write that as AB plus BA, remember, and I said that is what is the Hermitian combination. If you had a cross product of two operators, so we find x squared plus p squared to be 2IH cross, sorry, xp plus px, and this is Hermitian. So, I am just trying to say that if you have A dot B as operators given in 3 dimension, you have to, it is not same as B dot A, which you are familiar in your classical physics. This, when you go to quantum physics, this is classical. Quantum, you have to make it Hermitian, which means A dot B plus B dot A divided by 2. Is this Hermitian? If you just took A dot B, is it Hermitian? Not Hermitian. Why? Because A dot B dagger is B dot A. A is Hermitian and B is Hermitian, but A dot B is not Hermitian, it goes to a new operator. Whereas this one, A dot B goes to B dot A and B dot A goes to A dot B, so that is a Hermitian. So, and comes naturally in the commutator brackets, I did not do anything. Using the properties of commutator, I end up getting combination of xp plus px naturally, I did not get just xp, okay. So, the order really matters and you have to be careful with the ordering. So, just to reflash that slide, so the last where the ordering is done is the one which will help us to find the commutators of any products of operators. Let me stop here.